Welcome to Math 31. This is a lesson on one-sided limits. In one-sided limits, there's been a reference, I believe, to it earlier. It's taking the properties that we know about limits and looking at things a slightly different way. Ultimately, this is going to be leading us to a more technical look at continuity, which we've already dabbled in. But to begin, let's consider a fairly routine split function. So f of x is equal to x squared under certain conditions if x is less than or equal to 2, and then it's equal to x plus 3 if x is greater than 2. And you may note that the breakpoint is at x equal to 2. Now the breakpoint, you might recall, is where we switch from one function to the other. And normally, when we're dealing with one-sided limits, we are concerned with that breakpoint. In theory, we can do a one-sided limit at any value, but most often it's going to be a split function and at or around the breakpoint. So what we do, we determine the left-hand and right-hand limits as x approaches 2. So I did select that point, the breakpoint, and left-hand limit goes like this. The limit of the function f of x as x is approaching 2, and when we see the superscript of the minus sign, that means that we are approaching it from the left side, the left-hand limit. And then the right-hand limit would be very similar, except it's 2 plus. And anytime you see that sort of notation, it means that we're approaching that value from the right side. So we're breaking it down, left-hand limit, right-hand limit. And this one I'm going to really look at more graphically first off before we take a closer look. But this is what the graph would be, this split function. And here's 2. And the left-hand limit would be approaching it from this side. And then the right-hand limit would be approaching from that side. Now what's important with this is that we note that you're on two different functions when you're doing this. So the left-hand limit is going to be involving this, and the right-hand limit is going to be involving x plus 3. So left-hand limit would go something like this. The limit as x approaches 2 from the left side, and we want to be clear that we're dealing with the function x squared, because that's the function that is in operation when we're approaching 2 from the left side. And so the left-hand limit is going to be, well, we always start by substitution. So 2 squared is 4. So the left-hand limit is 4. And that's consistent with what we see on the graph as well. The right-hand limit would be the limit as x approaches 2 from the right side. And this time the function in play is x plus 3. And we start off with substitution, plug in 2 plus 3, and we get 5. Which also matches the graph. So that's all that we have to do so far. Now where this is leading us is this summary, this observation. If the left-hand limit does not equal the right-hand limit, such as in the previous case, as x is approaching a number, then we would note that the limit does not exist as x approaches that value. So another way of looking at that is if the left-hand limit is equal to the right-hand limit is equal to a number, L, as x does approach a value a, then the limit is going to be equal to L. Very important. So the left-hand limit must equal the right-hand limit in order for there to be a limit. Now we can tell this mostly by observation. So that's probably what you're thinking. Why take the time to break this down? Well, that's a reasonable point, but you are going to be asked to do it algebraically on an exam, for example. I probably won't leave it open-ended. Rather, you have to, you'll be asked to show both of them. Now, graphically, if we take a look at this, this doesn't have any numbers assigned to it. There's a, and if you were to note by inspection, the left-hand limit. So the limit of this function f of x as x approaches a from the left does not equal the right-hand limit. We can tell this by inspection. Here's the left-hand limit, here's the right-hand limit. They do not equal. So therefore, the limit of this function f at x as x approaches a does not exist. You have to be able to assign a single value to that limit in order for there to be a limit. Another way of looking at this is that the graph is discontinuous at x equal a. Now, things are not always that straightforward. Let's take a look at the next one. Now, we have a pretty standard looking graph. We've seen variations of this before. But with respect to x approaching a, we can actually get numbers for it. The left-hand limit is equal to, well, as we approach this function from the left, that is cruising down this direction, we are approaching what appears to be the number 7. And then the right-hand limit, as we're going this direction, is equal to 7. And the left-hand limit equals the right-hand limit, so equals 7. So therefore, the limit of this function f at x as x approaches a is equal to 7. So the left-hand limit equals the right-hand limit, so the limit exists. Again, by inspection, you probably would have been able to answer the question. One thing to keep in mind when you're looking at this is the graph is discontinuous at a, but that doesn't matter with respect to the limits. The left-hand limit is equal to the right-hand limit. Limits, remember, just tell us what's going on as we approach. They don't tell you anything about what's going on when you're equal to that number. Let's turn our attention to another algebra question. So this is the limit as a split function as x approaches -1 of x squared minus 3. And then x minus 1. Here you're asked for the limit as x approaches -1, which of course is the break point. And we've already done ones like this before, but just quickly run through it and then note the graph. The left-hand limit, make sure that your method is clear. You write this as the limit as x approaches -1 from the left side, and the function at this point would be x squared minus 3, so a quadratic. And this limit value, if you plug in -1 to it, is going to be -1 squared is 1 minus 3 is equal to -2. So, as always, when you're calculating limits, we substitute in first to see if that gives us an answer. And then we take the limit of x minus 1 as x approaches -1 from the right side. And if you plug in -1 now, we'll get -2. So the left-hand limit equals the right-hand limit equals -2. So therefore, the limit of this function f at x as x approaches -1 is equal to -2. Take a look at the graph. And we can see that they both equal the same number. So the limit really is just the y value, right? And we are approaching. And this graph is actually continuous because it's a filled-in graph. Now the next one is kind of an oddball question, but it does illustrate a point that's relatively important. Now I know when you're looking at this function, the limit of 1 over x minus 1 as x approaches 1, you're thinking right off the bat that there is no limit. You substitute 1 in, you get 1 over 0. So this question, in that regard, is kind of useless. But the bigger point is that we can still take left and right-hand limits of it. It's a little awkward, but we can do so. So as x approaches 1, what we would do for the left-hand limit is we would substitute in values. So I'll write this out. X approaches positive 1, from the left. 1 over x minus 1. So you sub in values, excuse the messy writing, sub in x values close to 1, but on the left. So you would substitute in, say, x is equal to, well, 0.9. And then you move closer. X is equal to 0.99. And, you even go closer still if you want, 0.999. And as you do so, you should get y values, and you're going to see very quickly that those y values start to dip quite a bit. So this is equal to negative 10, I believe. I don't have a calculator with me, but that seems reasonable. 1 divided by 1/10, and then this should be y is equal to negative 100. Check those numbers out, but I think they're correct, and etc. like that. So they go on and on. So there is, the left-hand limit appears to be going down forever. Negative infinity, I'll write that. And then you do the same thing with the right-hand limit. So this is the limit of 1 over x minus 1 as x approaches 1 from the right side. So you would be trying in values like x is equal to 1.1, and then x is equal to 1.01, etc. like that. And then you're going to see y is equal to 10, etc. like that. And what's going to happen is that you're going to see that as you approach that value of 1 from the right side, the y values are going to go up and up and up and up and up. So even though we already knew the answer to this question, we can note it again. The left-hand limit does not equal the right-hand limit. So therefore, no limit as x approaches 1. So you would only do this if you were asked to, and you would only do this otherwise if you couldn't figure out the answer to the question. And there are people among us who will do this for almost every limit question. Their understanding of the concept is good, but they just don't seem to have the math done very well, so they just plug in values as x approaches that to get that. Not a recommended method, but you can see that it does work. And here's the graph, and so it verifies what we had already expected. Now, a really important use of left and right-hand limits is absolute value functions. Absolute value functions have a very specific look. And so we're going to do a couple of them, but this first one, number 1, is the limit of, as x approaches 10, of x minus 10 absolute value over x minus 10. Now, I've gone to a more complicated absolute value function. The really basic ones aren't that interesting. But these do have a very specific look, and you have to know what you're doing with them in order to make these ones work. And the key concept with absolute value functions is that they always split into two functions. So even though this question is given to you as a absolute value function, it breaks down into a split function looking like this. So we get the limit as x approaches 10. 10 makes sense because you can see it doesn't exist at that value. And the one function, because absolute values always break into a positive and a negative, this is going to break into negative x minus 10, negative around the bracket, over x minus 10, if x is less than 10. And then the other half of the function is going to be the positive one, that is positive x minus 10. You don't really need a bracket around it, although I put it up, over x minus 10. And this is in play if x is greater than 10. So you need to know how these ones break down. So the negative would be when you're approaching from the left side. And then you do the left and the right hand limits. So the limit of negative x minus 10 over x minus 10 as x approaches 10 from the left, well, you're going to see that you can divide out by a factor of x minus 10, and this limit is simply going to be negative 1. And then the right-hand limit, x approaches 10 from the right side, is x minus 10 over x minus 10, the positive, and this one will divide out by a factor of x minus 10, leaving you positive 1. Keep in mind for this one, x is not equal to 10. And we would then be aware that the left-hand limit does not equal the right-hand limit. Therefore, you can write it like this as well. The limit of f at x as x approaches 10 does not exist. The graph looks like this. So it's a step function, if you think back to Math 10 or Math 20, whenever you look at those. So two linear graphs. They're clearly by inspection, it's discontinuous at 10. There is no limit there either. Now, they're not all like that. They all break down in that form, but you can get different variations of them. So let's take a look at one more that's a little bit different. So x minus 2, absolute value over x minus 2. So you need to be aware, this is the connection that you have to make, that this really is the limit as x approaches 2 of negative x minus 2, so a factor of negative 1 goes outside of the bracket, over x minus 2, if x is less than 2. And then the other one is positive x minus 2 over x minus 2 if x is greater than 2. And then work out the left-hand limit. The math tends to be pretty routine. This is the limit of negative x minus 2 over x minus 2 as x approaches 2 from the left. And as we've seen before, we divide out by a factor of x minus 2. That leaves us with just negative x, which I'll write this time. So a little bit more complicated than the previous one, 2 to the left. Plug in 2 now, and you'll get negative 2. And then the right-hand limit is the limit as x approaches 2 from the right side, and this time it's x minus 2 over x minus 2. And this would simplify to the limit x approaches 2 from the right of x. So when you plug in 2 this time, we get positive 2. So, in fact, again, the left-hand limit does not equal the right-hand limit. So, therefore, the limit of the function f at x, or whatever you wanted to call it, as x approaches 2, does not exist. I didn't graph this one, so feel free to take a look at it and see if it makes any sense to you. Not every absolute value function will have no limit. So you do have to check them out. They have a conventional form like the previous one, but it is possible the limit does exist. So that's it for this lesson. The next lesson will be involving continuity, which takes this concept, goes a little further with it. So thank you for your time.